real compression, they're on all three sides, right, they won't fail. You can crank them up as high as you go. I mean, at least they won't fail at anything we would consider reasonable pressures, right? I mean, obviously, if you get to neutron star black hole densities, right? I mean, where the laws of physics get really weird, then things get different. But for anything that we would run into in sort of on the surface of the planet engineering, they don't fail progressively. What materials do is they get out of the way, which is why we say they fail in shear or they fail in buckling. And so doing this, what do? They go, hey, I don't like to be here. I'm going to be over there somewhere, right? And they'll get out of the way and let the structure fall down. So that's sort of the nature of these. Okay, that was easy, wasn't it? You think you can do that? Now, you think you can model out as a solid and do the same thing? Yeah, I think you actually can. I have faith. I have faith. You have faith.
Yes.
No faith. No faith. Okay. Okay, so we have to have faith in here. Got to have a little bit of faith, right? Just a little bit of faith. Okay, so I'm going to go ahead and go back to my simulation and go do a new study here. And instead of doing a buckling study, I'm going to do a frequency study. Okay? And say, okay, and now I get to do the whole thing again, right? I get to tell it what material it is. Oh, and I'm going to tell it it's steel, because I like steel. I know we're Boeing country when they make everything out of aluminum, but I like steel. Fix some geometry down here at the bottom. We're going to make the symbols really big. We've done this before. Okay, and then we're going to put a load on the top. Okay. And we're going to put it on the top, up here. And we're going to define it from someplace convenient, like the top plane. And then we're going to assign it out of plane. And then we're going to make the arrow real big. And then we're going to tilt it to go the other way. Okay. And then we're going to say that's good. Okay. Okay. And then we're going to mesh this thing up. And then we're going to say, done the study. And what I get is,
With 1 pound again?
just 1 pound, yeah. And I get this thing out here that says, okay, it's going to oscillate at, what?
1.7.
1.75 hertz. Okay. Which means that in a stiff wind, it's going to go back and forth, right? About a couple of seconds, right? 1, 2, 1, 2. So it's going to sway a little, but hey, it's a 40-foot pipe. You want to be up on top of the 40-foot pipe? Nobody here is into flagpole city.
Harvey Danger.
What's that?
Harvey Danger.
Harvey Danger? Not familiar, sorry. Missed my So again, we have, we'll look at different modes, and we can look at different shows. This mode is a 1.75 hertz, and of course I'm going to get another one that's out of plane. That's going to be doing the same thing, 1.75 hertz, right? There's one in one plane and there's one in the other plane, and they're at the same frequency because it's a bloody pipe, right? I mean, they separate out the two planes because there are, if it's not a symmetric section, if it's like a piece of rectangular tubing, which is what I should have used, something to make life interesting, right? They'd have been different frequencies, okay? right? Would have been slightly different frequencies. I'll have to go back and do that. And then we can go look at the higher modes, right? And the higher modes are now up at 10 hertz, right? So there's 11 hertz frequency mode where it's oscillating back and forth, right? Beginning.
It's going back and forth, but that's fine.
Yep. Yep. Now, it's not oscillate very much, right? The higher frequency ones are typically the amplitude of them much smaller, right? As a rule, those are actually, but that's another harmonic mode that's in there, right? And there's basically an infinite number of them, right? There's a fifth mode, which is up at 30 hertz, right? 30 hertz, right? So, and of course, there's, okay, so that's the 5 that it did. Let's go, it's actually a good question back there. I'm gonna go back to my model here. And I'm gonna go pick on this pipe here and go, come on. I want the, oh, come on.
If you go to the sketch,
I have to go to the Wellman, or is it on the sketch?
well, if you right click under the pipe, if you expand the pipe, that sketch says.
Options.
Frequency.
It's not down here. It's not letting me edit it. And I'm not sure if I need to edit it. Well, I'll just blow it away. Why are you not cooperating?
Are you supposed to edit the pipe underneath that?
I tried, but it didn't
That
let me
one?
anymore.
You cannot.
The sketch, what if you right click the sketch? Because that's what.
And I could show it and I can
Yeah.
zoom to it, but it doesn't let me do anything with it, right? So, now let me see if that happens if I hit delete. Doesn't like that either. Cancel. It's not very nice of it to not let me edit the thing. I think I must be in a strange mode. Are you in the same mode that I'm in? Yeah, you can't do anything with it? Right,
No.
so, okay, well, that's annoying. So it's not
Delete
letting
it.
me.
Just delete and redo.
Click under features and edit feature.
What? Oh, that's right, okay, you're right, I was in the wrong one. Is that gonna help?
Maybe.
Doesn't seem to help when you're under that as well.
Just get rid of it and redo, I guess. I trying to.
Yeah, it's not letting me, I really wanted to change it to a different cross-section, so we could go play with it at some different, but it's not letting me, I can't even, I don't think I can even delete it. It's not letting me even delete it, which is really not very nice of it.
Yes, you can.
Yeah, we can.
Yes, you can delete it.
Did you
Yeah.
delete it?
Yeah, just
Your
click
options
delete it.
Different, right click?
Just
Right click?
delete it. Oh.
I think need to be right click.
Yeah,
Right click.
it's not.
No, just click on it and delete button.
So if you
No, I
just
can have
go to
options
insert
in there.
weldment and you add a new one, does that just?
Yeah, well,
Put it on
I
top?
could probably do that, but then it'd get rid of the old one. I could pick this.
Yeah, you can hide that one and then just use the sketch again.
Yeah, I can. Certainly can use the
Anything
prior
better.
sketch, right?
Yeah, and then go back to
And
insert.
a new section.
Yeah.
And then I'll have to, let's go for some tubing rectangular. And what size do we want? Let's go for something like, how about by 5. That sound like a nice one?
Hmm.
5/16 wall, that's a fine size. Oops, I just want you. Okay, and, we'll take that. And now I have 2 of them here. And, ooh, now it lets me edit it. Okay, well, that's fine. Now let's be deleted. Yes. Okay, now I got the tube, I can go back to the buckling now. And, yeah, I think it's all good. I need some applied material. Right, we'll do I just made it a rectangular tube is all I did. Right, and, I think it's just, no, I'm wrong button. I think I just need to recalculate the joints. Calculate. Okay, there we go. Okay. So I don't know why you're unhappy. Okay, you're fine. Okay, yeah, you're fine. Okay. And the force is applied. Come on. Force. Oops. Yeah. Okay. And rid of you. Yeah. Why are you not happy? Okay. You're perfectly happy. You got, oh, I need a joint. Right, wanna pick on you. And wanna pick on you. Nice joints. Other direction, right? And the symbols already needs to be big, cause we're doing this, so, okay, we're just, playing with this, okay. So now we can, make the mesh this guy, and then run the study. Okay, and, if we go to mode shape 1, we still have this, now we notice my load factor is down about 11,000 pounds, right? 11.5 for this particular one, right? I got the same load, but when I go to the other direction, what's gonna happen is I have to look at the other plane, right, over here. I still have the same mode shape, but now my load has gone up to 34,000 pounds. What's happening is because it's asymmetric, it wants to bend the same fundamental shapes, right? But it takes a lot more to fail in one direction than it does the other direction. So it's buckling in the skinny direction, right at 11,000 pounds, or predicting that, and it's buckling in the wider direction at the 30,000 pounds, right? And we'll see that same behavior the rest of the way up, right? Here we have one that's the 3rd mode, and let's go to the 4th mode, just because it's going to be in one of these other planes. Right? So it's not deforming very much. Come on, you can. That's because the scale's not very big. But, come on, is it in, one of those? There it is. There's the next mode up, right? See, it's deforming at 100,000 pounds instead of at 30,000 pounds. And that's the mode that'll be in the skinny direction, but it's the more complex mode. And we'll just follow them on up now. There's the 4th one, right? It's almost at 30,000 pounds, right? And then there's a 5th one up there, which is probably in the other plane. Right, they go back and forth between the planes. There it is. And that's the one in the, it's actually the thick direction, but it's a lower mode shape. It's because it's easier to bend it in the other one. And this is not, I wanted to do this just to have an asymmetric cross section. So you can say these mode shapes are gonna be the shapes are basically similar to each other, but they're happening at different values if the cross section's asymmetric. When it's round, of course, what do? We get values that are all the same, right? Because it doesn't care, right? It's going the same way in both ways, right? Okay, and then if we do the frequency analysis, which I'm going to have exactly the same problems, and it goes, oh, I'm so unhappy. You're so mean to me. Let me recalculate all the joints. Yeah, okay. Gonna recalculate the joints. Yeah, I know. Let's see if I can't make the fixture here. Not fun. I want to edit that. Right. Yes, I know you're unhappy. And that's because I want you to fix down there, right? Okay. Now you're happy. And I get you. And it's just because whenever you recalculate them, it doesn't know where it is. Right, and now it's happy. Should be happy, and we should be able to create the mesh. And then we run the study. Oh, you gotta say I didn't find material. Okay. Steel. Okay, and we see we have one it's not showing in this view, but we'll pick one of these other views. We're gonna have a fundamental mode. This one's down at about a little under a hertz. Basically, it's at a hertz, right? So what's it gonna do? It's gonna oscillate back and forth in a second, right? So it's a 1 hertz oscillation in there. If we look at the next one up, right, it's gonna be in the other plane. So you wind up going back and forth between the planes. Here's the other one, and it's at 1.7 hertz. Sort of close to where we were with that round tubing, right? Because round tubing, the first one was about 1.7 hertz. And then if we keep going up, they're gonna get higher, right? Come on. There's the third one. Right, and now we're up at 6 hertz, right? We're getting another oscillation where it's going back and forth from the top. And there's the fourth one, there's the fifth one. It's up at 17 hertz, and these will be really small, so that's all they got in the fifth one. Fourth one's gonna be that other same shape in the other planes. Rolling around, so that's that second mode shape that we're getting there. Okay, so does that make a little more sense, what we do? Now, can we do the same thing if it's a solid model? Yeah. Yeah, we just put a force on the top and see what it does, right? See if it does the same. Can you calculate the buckling strength of that from Euler buckling?
Can you compare to SolidWorks designs?
You're using a computer to compare a
Can
computer?
the computer compare?
There's a design results, design study thing
Where you
in
can load two
SolidWorks
models
where
and-
they're designed to look at different variables, and in all honesty, I haven't played with it.
What's that
Okay.
compare results thing? Or
I don't know. I don't know. I
You
do
can like only do one result at a time.
compare results. Okay.
Not much. Oh, you can see in the different modes?
I guess you just showed you all 4 of them there, right? Okay.
Gotcha.
So apparently that's what compare results does, okay? Probably makes fancy graphics for reports too, right? Color pictures to keep managers happy.
Yeah.
Yeah. We like that, don't we?
Mm-hmm.
Okay, so buckling looked pretty easy. good question. How do I deal with the sign? Okay. Well, I wouldn't make it as an assembly. Okay. I'd make it as one piece. Now, let's have a little discussion of the sign. Just you might say a sign of things to come.
You can
Okay.
not
Okay. Yes.
put it on top of the pole,
Well, what's the sign doing?
making it.
Putting a torque on it.
It's putting a moment on it, right? It's putting a moment on it. It's putting a bending moment on it. There's putting bending moment 3 feet out, 500 pounds, right? Right. There's a bending moment on that thing that's out there, 3 feet out, 500 pounds, right? It's putting a bending moment on that darn thing there. And what's that going to do? Well, is that going to help it with its buckling, or is it going to make things worse?
Make things worse.
It's going to make things worse, right? Because it's the Euler buckling always assumes that everything's loaded right along the center axis, which is what we've been doing. And of course, reality is it's never that way. Now, the initial tendency is when you do buckling is to go, oh, okay, well, sure, it's not bad. I'll just make this a big plate. Just make it a big plate. Okay, make it some big flat thing. Certainly you can do it in the solids, right? Not really in beam, but certainly in a solid form. We'll make it a big flat plate. If I want to, I can give it weight, or I can put a force out in the middle of it that's 500 pounds, or whatever I feel like doing with it. There's an issue with this though that shows up, and it shows up really, really quickly. And that is that, you guys should be all too aware of this. And that is that if anytime you have things that are plates, they can buckle, the plate itself can buckle long before the underlying structure does anything, right? And I mean, you see this all the time on anything that's got sheet metal skins, right? If you torque it or twist it or pull on it, what do? You get failure of the skins, right? They buckle because they basically won't take a compressive load at all, right? I mean, they just go, no, I'm not taking the compressive load. I'm going to buckle because I'm really thin